the circuitry configured in Logism that makes our 8-bit CPU work. So starting at the high level, we have a ROM memory module which has data bits of 16 and an address bit of 8. Those correlate to our command length and the size of one of our registers. So essentially, the command at the given address in the ROM module, which defaults to address 0, is fed into our CPU. And then on the other side of the CPU, we have outputs of register RH, which we feed back into the ROM module. Essentially, this feedback loop lets our CPU read commands from memory and then manipulate which command it's on. Register RH, which we'll see in more detail in a minute, that register is a counter register, but I also allow it's configured to allow writes, so you can apply a jump assembly operation and jump to a specific address in memory. Obviously, with this configuration, the ROM is fairly limited. Since we only have 8-bit addressing, we can only access 255 instructions. On the output side of the CPU, we also have register RF, which you can see I've wired up to this little 8-bit to ASCII conversion circuit, and that goes out to our output display. And then just to see what's happening, it helps with debugging, and it's also kind of fun. I have this matrix, LED matrix set up to display some other register values. Now, output from the 8-bit to ASCII circuit is also this additional clear bit, this enabled bit that goes into the ASCII to 8-bit output, and here's our keyboard right here. So this bit right here, when it gets triggered, it will trigger the reset on the keyboard to clear the keyboard's buffer, and then on the keyboard I have that set to a single character buffer length, so you can only enter one character at a time. Then the ASCII to 8-bit basically takes the 7 bits of ASCII and attaches a 0 high bit to it, and that is fed back into the CPU as register G. So H comes out as your memory address, the command comes in from the memory, G is the input from the keyboard, and F is output to the display. So looking inside the CPU, we have the 16-bit command feeding into our control unit. This is that register G that I mentioned earlier. That's kind of a constant input register, if you will, and then these are the constant output registers coming out of the CPU that you saw wired up earlier. The control unit is responsible for taking that command and basically parsing it out into the operation, which is going to trigger one of these different operations right here, and then the input registers A, B, and C. C is an output register, but the registers A, B, and C, along with an input constant in the case of commands that take one register and one constant. And you'll see here these two commands I left unimplemented. It says SBT and GBT, but this is what I would intend to build setmem and getmem operations with. These feed directly into the ALU, these top operations, because they're all ALU operations, but there's a couple operations that are not ALU operations. They are the move. This here is a flag to just that flags if it's an ALU operation or not, but the move operation, the set operation, the C move, conditional move operation, and the C jump operation, those are all not ALU directly ALU dependent, like an addition or subtraction. So you'll see them wired in a bit differently. Originally, before I added in those operations, this was a bit more simple, but adding those in, I probably needed to move some of this wiring into the control unit. Instead, what I did was I added this additional swapper circuit, which I'll cover, that makes a few adjustments to the inputs and outputs before they go into the register. And then on the flip side, a couple of the operations will take an output from a register and then bring it back into the registers. For example, the C move will check the value of a register, and if it is equality, then it'll allow the register to be written, another register to be updated with a register from another value. So inside the control unit, this is what it looks like. We take the 16-bit command, we split off the first 4 bits. That becomes one of our operations, as you can see here. For any of the operations that use the ALU, we also flag this ALU output. And then we take the next set of the next 12 bits and we split them into 3 registers, or for certain operations, we take the middle 2 set of 4, so combining those into 8 bits to get a constant value that we write or that we pass on to the register and ALU. So for example, the set operation has a 8-bit, the middle 8 bits are combined into a constant value like set 154 to register A. The last 4 bits identify the register that's getting set. So this is what the AL or the control unit inside the CPU looks like. Then what this swapper thing is doing is basically for certain commands, we're flip-flopping things around so that because we only have 2 input registers and I wanted the commands to be consistent. So in the case of set, your the third argument is output register C, but in the case of, you can see here, C move, set C to A when B equals 2. We just moving these registers around a little bit. Like here, for example, I think this is a good example. So C move gets register B, and then we actually compare it to the value 2, and if it is the value 2, then we allow register C to get updated with register A. So then inside the register circuit, the registry bank circuit, this is what it looks like. We have a couple constant input going to register G, so that is always getting updated. And in fact, I originally had a register in here and I realized that this constant input can just be passed out. We don't actually need to store the value of it. Then we have our input value and input register. We have a register A and register B, and then the clock. This is register H, which is, you can see, is a counter. These other registers, I actually created a custom register circuit, and you can see that down here. It's really just a flip-flop, and then I have simplified some of the wiring and rolled it up into this circuit so that I don't have to have a billion buffers in my register bank. So it takes an input, it has a write flag, it has A flag, B flag, and then a clock. So the input value, if write is on, it'll write to the flip-flop. If A is on, it'll output to the A output. If B is on, it'll output the value to the B output, and it always outputs to the constant output. So you can see that here, basically, in each register, we're always outputting the constant, and then in certain cases, if their flag is set, then we'll output that register's value to this output A or output B, or both in some cases. So that's the register bank. Then inside the ALU, this is what the ALU looks like. At this point, we are no longer talking about registers, we are talking about values. So we have an A value, which is 8-bit, a B value, And then we have a set of flags to determine which of the operations we're performing. So compare, subtract, add, decrement, increment, logical not and or bit shift left and right. So if you're doing a comparison, you see that comes down here. We have our equality circuit, which is an 8-bit equality. If you're doing subtraction, that comes down to this addition circuit, which handles both addition and subtraction. The left shift circuit and the right shift circuit, and those all output to this output. We have a carry flag and an overflow flag. I'm not doing anything with those at this point. So you can't see if there is an overflow. There's nothing that shows on the system. So quickly looking at how these addition, equality, and left and right shift work. Basically, 8-bit equality is taking two 4-bit equalities. It's saying if the high bits are equal and the low bits are less, then we're less. If the high bits are equal and the low bits are greater, then we're greater. If the high bits are greater, we're greater. If the high bits are lesser, we're lesser. If the high bits are equal and the low bits are equal, then we're equal. The 4-bit equality does the same thing. So I have a 1-bit equality circuit. So it has 4 of these 1-bit equality circuits, and it does the same thing, but with 4 instead of 2. And then the 1-bit equality circuit is very simple. It says that if this bit and this bit are the same, it's equal. If A is high and B is low, then it's greater. If A is low and B is high, it's lesser. In a similar fashion, I set up my adder. So basically the 8-bit adder takes 2 values, and then it uses the 1-bit adder and their chain to track the carry flag. So 1-bit adder, add 1 and 1, we get 0, carry the 1. Add 1 and 0, you get 1. If you're already carrying a 1, then it's 0, carry the 1, etc. So that goes to this output. And then at the end, we have our overflow and our carry flag if we surpass the 8 bits. That is our ALU and our CPU. I'm going to go back up 1 level to the system. And I think that is about it. These 2 circuits right here, again, they just, so the 8-bit to 7-bit takes your 8-bit register, and then pulls off the low 7 bits and then passes the high bit to this clear flag. And then the ASCII to 8-bit basically does the opposite. You take the 7 bits from ASCII, add a constant 0, and then I'm not really doing anything with this. I probably could have gotten rid of it, but I left it in place. So that's how the system works. Quick overview of the circuitry.